Slide set number 12. When you say footing, usually it refers to it as a pad. So pad is the same as a footing. Foundation is going to be like general terms, if you like. And it's going to be this structure member, which is going to get connected between the columns or the walls and the soil. We have this slide that we looked at before. It shows reinforced concrete building. You have the first floor, you have the second floor, all supported by columns. And also you have this wall, reinforced concrete wall. And then at the end, this column needs to be supported here with the footing. So supported here by a footing. And the wall also is going to have this continuous footing below it. And this footing, or this wall footing, is going to be the interface between the concrete structure and between the soil. If you don't have this footing, what's going to happen? The force is going to be concentrated right below the column, and the column is just going to be penetrating the soil, and the entire bin is going to be settling. So you'd like here to provide enough contact area, which is this contact area between the soil and the footing. And this contact pressure, which means the pressure on the soil itself, needs to be within certain values. This allowable values, it is usually determined by a geotechnical engineer or soils engineer. And as a structural engineer doing design for the footing and the column and the entire thing, I just need to take this value from the soils report or geotechnical report and use it in my design. Same thing for the wall footing. Just imagine if the wall is going to be very thin here and it is not thick enough to distribute the stress on the soil. Now, this wall here is going to start to sink. It's going to start to penetrate the soil. Because in this case, the stress is going to be extremely high below the column or below the wall. And when the stress becomes very high, the actual stress is here. Once it becomes very high, the soil is not going to be able to support it. That's why you need to keep it within the allowable soil bearing pressure. I'd like to hear from you. Has anyone taken soil mechanics or soil design, foundation design course?
Yes.
Yeah.
It's
Okay.
soil mechanics.
Soil mechanics. Has everybody taken soil mechanics class?
Yes.
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 Anyone who has not taken it? So let's make it the other way around. Anyone didn't take soil mechanics class? Okay, very good, Miguel. You're taking it now. So just want to be sure that I'm not talking about something like out there. I mean, something that you have no idea about. So it's good that you understand the soil, and yeah, I'm gonna say here, good understanding to the soil. So when it comes to the soil here, you need to find out the allowable soil bearing pressure. To find out the size of the footing. Size of the footing means the length by the width. Because if you think here about the contact pressure between the footing and between the soil, it's going to be equal to the column load divided by the soil or by the contact area between the soil and the footing. And with that, you're going to have the actual soil pressure. Now, you want to be sure that this actual soil pressure is going to be within that level, which are going to be determined here based on the soils report or geotechnical report. Now, what happened if you go here beyond the allowable soil bearing pressure? More sediment is going to happen, excessive sediment, which you don't like. No one likes this. Same thing for a different building. You have some columns, and here also you have a wall. And then at the end, at the bottom of the column, you need to have this footing, and the size of the footing length by width is going to be based on the allowable soil bearing pressure and the column load. How about the thickness of the footing? You're going to say thickness of the footing is going to be based on the design of the concrete member, which is in this case the concrete footing. And do we need to have reinforcing in the footing? I'm going to say absolutely. We're going to be coming through it very soon. Here's another picture for a building like a section through it. and it shows a basement level. So this concrete slab is going to be the same as a street level. You have a second floor and maybe a roof here. And we're cutting through some beams at the roof level. Here's a concrete slab that you're going to be cutting through, supported on a few beams. Some beams in the middle for some artificial reason, but they don't really provide lots of structural like value to our building here. And then we have this concrete slab, which is at the grade level with some beams. Then we have walls. We have columns. You see here, we have a column that runs through, and then at the end here, you have some footings, right? You have some foundation, continuous foundation, sometimes just a pad. A pad means like rectangular pad or a square pad. It is not, it is unlike having continuous wall footing. Now let's think here about the load path. Where is the load coming from and where it goes to? The load starts here at this slab level. So sometimes you have surface load like uniform load. Sometimes you have point load. Sometimes you have line load. It depends on the item that you're trying here to support. This slab here is supported on 4 edges with beams. So what's going to happen? The slab is going to be taking this load and distributed to be kind of uniform load when it comes to the surrounding beams. So first load is going to be coming from here, this applied load, with the self weight of the slab and any other additional dead load that you'd like to add. And then it's going to get transferred to these 4 beams, and then the beams is going to be supported on 4 columns. So if you think here about the beam, like the standard way that you used to do in the structure analysis, you take this beam from here to there, another beam from here to there, and then you look at this uniform load, you do the analysis, you find out the reaction from both beams. So again, here's one beam, and here's the other beam. It means this support, which is a column, supports both of these 2 beams. And whatever reaction that you find from the right beam and the left beam, you just add them up and then you put it to be supported by the column. Now you should be able to design the column here at the bottom of it, right? You say, here's the total column load. Now this column load and the self weight of the column and this footing, the entire thing and all of this loads is going to get supported by the soil. So if you take all of this column load, the entire load here, right? Divide this by the contact area. Now, what is a contact area? If I may zoom in, this is going to be the contact area between the footing and the soil. I'm going to call this to be A. So I'm going to say A is going to be the contact area, right? And P is going to be the axial load. So I'm going to say the stress right below the footing, I'm going to call the stress is going to be Q, equals P divided by A. This is going to be the actual stress below the footing. It is not a soil property. What does it mean by soil property? Soil property means, for example, unit weight of the soil. You call this a soil property, one of the soil properties. You say, for example, allowable bearing pressure of the soil, which means a limit of the soil. This is going to be what? This is what you call here a soil property. Similar to what we have discussed in concrete and steel for the reinforcing. We say concrete strength is, let's say, 4,000 psi. It means the strength of the concrete at 28 days is 4,000. When we say yield strength of the steel is 60 psi, this is going to be one of the rebar property. Is going to be start to yield here at 60 psi. This Q, which is P over A, it is not a soil property. This is actually an actual stress right below the footing. We have another value that we call Q allowable, which is going to be the allowable soil bearing pressure. This is going to be one of the soil properties. So I need to understand the difference between the two. This Q is going to be based on demand. So this is going to be like demand pressure. The Q allowable is going to be the allowable pressure. So we have here 2 issues. Number 1, we need to figure out the size of the footing, length by width, because I need to find out this contact area and be sure that I'm not going beyond the allowable soil bearing pressure. So I'm going to be calling this is going to be actually soil design, because the allowable soil pressure, it is not of the concrete, it is of the soil below it. So with that, you're doing here soil design. It is not really concrete design, but to work on the concrete footing thickness, right? The thickness here, and the reinforcing, this is going to be concrete design. It's going to be member design, if you like. Any questions? You're good? All right. I have your 3D picture for the same building that we cut through. This is the same as this building. And look what happened here. Some of this concrete footings right below the column. Then I have some grade beams. You see this beam here? We call this grade beam. This beam is to reduce the settlement, and it connects between the footings, between each footing and the other one, to connect them so that if one of these footings want to settle more, it's going to have a structural member to stop it. And this is going to be based on the structural analysis and the structural design. Some cases we do it, some cases we don't. It depends on the level of soil pressure value and the potential of settlement. Below the footing, you're going to see here a continuous, below the wall, you're going to see a continuous footing. See this? Because you have continuous load. So for in this case, you need to have here continuous footing. Here's the footing. If you like to look at one of these footings and the concrete column right above it. So in this picture here, this is going to be the column itself. And the column itself includes rebars, vertical rebars. We call this dowels because dowels, this is not the column rebars. This is just the dowels that connects between the footing and between the column. And of course, we're going to have ties or stirrups because this is your tied column, the way that you see it here. And then we have also reinforcing bars in the footing in both directions. And as you see here, the reinforcing bar looks like this, like a U shape. And you see this goes in both directions. In the plan view, you're going to see the rebars running in both directions. And of course, in this area here, the rebars going to be running below it. It's just shown here to be like this light or white area, just to be able to show the reinforcing bars of the column, right? But in reality, all of these bars going to be continuous rebars. Now, when you look here at the column rebars, in this elevation, here are the column rebars, some ties and stirrups, and here's the footing. Now the question is, why do I have the reinforcing bars at the bottom and not on the top? In this simply supported, or in this, it's not really simple support, in this concrete pad. Does it mean tension is going to be at the bottom and not on the top? Most likely. Okay, so yes. Tension usually in a case like this is going to be at the bottom. Another footing, very similar to the one before it. Exactly same design. And now all of a sudden, I see here a new mesh. We call this mesh. You see the top, I have a bottom mesh and it has this hooks. At the end, you have a hook. At each end, you have here a hook. But all of a sudden here, I'm adding top reinforcement. And I'm thinking here, why would I need top reinforcing if I just stated a minute ago that all the rebars on the bottom is going to be in tension? It means the top is giving compression. Why would I need any top rebars? I'm going to be talking about this in a minute. So what happened? You're going to be starting here to apply vertical load on the column, and this going to be the reaction. It's going to be this uniform stresses coming from the bottom. If you take this P again, this going to be the axial load, and A is going to be the contact area between the soil and the concrete footing. Q, which is right here, this is stress here. I'm going to call it Q. It's going to be equal to P over A. This Q, which is P over A, I'm going to call it actual stress. Between what? Between the footing and the soil. Now, which one starts first? Someone's going to say, do I have this stress that starts first? And this going to be the reaction. So which one is the action? Which one's the reaction? So I'm going to say the action is going to be the load coming from above. The reaction is going to be this load coming from below. And this reactions, once you put it in this footing, the footing is going to start to deflect this way, as if you have two cantilevers. And your critical section for moment is going to be right here. And also you're going to have another section right here. It's going to be at the face of the column. Someone's going to say, why don't you take the critical section to be right here? And I say, you can, but in this case, where's the depth of the footing? Which depth here is resisting the moment? Yes, say the moment in this case is going to be, if you like to call it, is going to be a negative moment because it's going to be right here at this section. But someone's going to be looking at this and say, when the tension is going to be the bottom is going to be positive moment. I'm going to say, okay, but looks like a cantilever. And people used, when they see a cantilever, they call it negative moment. But this is fine. This is called here a positive moment. This would be fine. At this critical section, the depth resisting this moment is going to be the thickness of the footing. It's going to be from here to there, to the location of the rebar. Does this make sense? It's going to be the depth resisting. This is going to be D, your D. When you do your analysis and concrete design, this is going to be your D. But if you take the critical section right at the middle of the column, now the depth resisting this moment is going to be actually the entire column height. It's going to be going all the way to the column height. So I'm going to say, no, this cannot be. So this is going to be my depth, and my critical section is going to be at face of the footing. So I'm going to go back here. Now I need to determine where is that section. Let's say in a case like this, I'm going to say this section again is going to be at the face of the column. But in this 3D picture, this section is going to be right here. Right? This makes sense? At the face of this column. You're going to have another one which is running this way at the other face of the column in this direction, right? So in this case, you're thinking about the soil pressure is trying to push this up, push this side of the footing up. And what's stopping it is going to be this column. So in plan view, I'm going to put the critical section for the moment is going to be right here. And the other section, I'm going to say the other section is going to be here. Now, I guess if this length, which means this cantilever length is going to be the same as this cantilever length, I don't really need two sections. One is going to be enough because the moment at both of these two sides is going to be the same. And the reinforcement that you put here at the bottom in this direction is what is resisting this moment. So here I'm talking about all of this reinforcing, right? All of this. All of this reinforcing is what is taking this moment at this critical section, right? See, now it makes sense. This piece here wants to lift up, so I'm going to put it in the box. So I'm going to say this piece, this is going to be here. This area here is lifted by the pressure from the underside of it, pushing it up, this pressure, which is the same as this pressure. So this pressure is lifting it up when it comes to this critical section. This is good. How about this reinforcing here? What do we design it for? You're going to say we designed exactly for the same thing. You're going to say, I'm going to have here a critical section for the moment. It's going to be at the face of the column in this direction. So if you like, this is going to be for the rebars in the X direction. So I'm going to call this to be the X direction, right? So this section is going to be critical section. The rebars in the X direction. Now, where are these rebars in the X direction? We're going to be saying this. All of these rebars, the rebars is giving the X direction. How about this critical section here? You can see this critical section is going to be for the rebars in the Y direction. Now, which rebars is giving the Y direction? You can say this includes all of these rebars. All of these. Considering that this piece of the footing wants also to lift up. If you have a point load coming this way, this piece here wants to lift up, which means this is going to be like bifolding. You have here bifolding mechanism. This side wants to lift up, and also this side wants to lift up. Any questions on this section? In both directions? And the reason that we need reinforcing in the X and Y direction is because you have this footing is like 2D element, and each side wants to lift up. So you need to have a design for this critical section, and you say this is going to be enough because in this direction for the Y rebars, because this section is going to be the same as this section here. And in the X direction, I'm going to have this vertical section, right? Which is going to be critical section for the rebars in the X direction, which is going to be this rebars running this way. Okay, I guess now I have a feeling for what this pressure is going to be doing to my footing, and the reason that I have the bottom rebars and not the top rebars to be used. Now the question is, why would you need here any top reinforcement? I'm going to say sometimes this top reinforcing is going to be helpful during construction because you'd like to brace this column rebars during construction while you are putting the concrete. So you're going to put some rebars here on the top anyways. And these rebars, they can count when it comes to the minimum reinforcing ratio. And also, just in case, if you need the help of this compression steel, you can use it if you want to. But mainly, it is done for construction. You're going to have few rebars running in both directions. It's not going to be that many, but generally speaking, just for construction purpose. And also, you need them for the minimum steel ratio, because this minimum steel ratio is to reduce the amount of cracks, shrinkage cracks in the concrete. So you don't want to leave the footing like this, all the top area here of the footing to be empty of all, any rebars. You'd like to put some rebars in both directions. This is actually a picture of an actual project. So here are some pads. It says F10. Usually F10 means that the footing itself is going to be 10 feet by 10 feet. Look at this. F10 is going to be 10 feet by 10 feet. Thickness is 24 inch. It has the top reinforcement. If you look here at the top reinforcing, now which one is larger, number 7 or number 5? Hey guys, are you there?
Number 7.
Number 7. So you see here, I have number 7 in both of the two directions of the footing. Let's say X and Y, or longitudinal and short direction. It just happened that this footing is square footing. So I have here 9 number 7 each way, which each way means each direction. And 4 number 5 is going to be in the top. And the reason that I have this 4 number 5, they're going to help during construction, because you need to brace the vertical rebars of the column to something there. So I'm going to add in here some rebars. So this here from an actual construction document. And you see here the thickness of the footing is 24 inch. We designed this thickness. We came up with it, and this gave you the total thickness of the footing. So you see here we have plenty of footings, and the contractor, that picture was taken at the site. The contractor would like to do this in one shot, right? So they put the concrete here in one shot, and this shaded or hatched in his way here, he'd like to do it in the second pour. So we said, okay, it's gonna be up to him. We don't care. He can pour it in any sequence he wants.
The footing schedule you were just showing us, what was the difference? The bottom reinforcing and the top reinforcing, is that for the beams or the?
Let me take you back to the previous picture that I was just talking about. The bottom reinforcing is what's taking the tension. This is why it is heavier than the top reinforcing. And as I mentioned, when we were looking at this one here, I said the top reinforcing is needed because you need to have some reinforcing bars to help in construction to support this vertical rebars. And also it's going to help you in the minimum reinforcement. So you're going to be throwing some rebars here anyways. And if you wait a minute, I can show you some pictures from the actual construction and to explain to you why I need this top rebars to be provided. It's not going to be that many, right? It's not going to be the same as the top reinforcing, at the bottom reinforcing. If you see here, the bottom reinforcing is 9 number 7, plenty of rebars. The top is going to be only 4 number 5. Okay?
Thank you.
No problem. Let me show a picture here of the actual construction. You see here, it does look pretty, right? You're going to see, wow, they just cut the soil and then pour the concrete. I'm going to say yes. Now, where is the form? Don't they do any form work around the foot? I'm going to say not really, because it's going to cost them money to put this form work. It is cheaper if they give you, for example, I'm asking you for 3-inch concrete cover, right? So they give me 6 inches. And I'm going to be okay with it. I mean, as long as you provide cover more than what I need, I'm going to be okay with that. So we should be fine. I mean, having this through the soil or through a hole in the soil is going to be acceptable to us. Look at the rebars. The bottom rebars, you have them with hooks, right? Running across in both directions. And look at the top rebars. Now, this vertical rebars, you need to brace them. Otherwise, they're going to be collapsing in one side, which can just falling. So you need to have some rebars in this direction, at least at the column location. And this can be the column dowels or rebars, right? That's why I need them. And this is the reason that the top rebars are not heavy. Yeah, go ahead. Go ahead, please.
Yeah, I always wondered, like, does having the spacers provide a place where water could potentially like seep through later on or into the concrete and then corroding the rebar?
You mean from the side?
In the bottom, because you know how in the bottom they have those little gray spacers to provide the clear cover on the bottom of the footing?
Yeah, this blocks, right? This blocks.
Yeah, I always wonder, like, is that a potential place where water could go through, like,
This is why we have plastic, but here they are made out of cement, so it's gonna be the same as a material of construction. So sometimes you do it
oh,
plastic, sometimes you do it out of cement, so they blend in with the cement.
got it. Thank
Yeah.
you.
And if
My
you have
fir-
problem with water seepage, if this can be an issue on a site, you don't really just do this. Once you come here to the bottom of the hole, you need to put moisture proof, right? You need to isolate here the footing, the concrete footing, right, from any moisture. So what you can do, you can put the alignment, you can put it right here below the concrete footing and then build on the top of it if this is going to be truly an issue.
Got it. Like that geotechnical fabric and stuff.
It's going to be like visqueen, it's going to be like plastic. The
Oh, okay.
the fabric that you're talking about here, it is not mainly for the moisture proof, it is for different reasons. All right.
Okay.
So this is here one of the wall footings, and you see it's going to be like continuous footing. That was an early stage of construction. And let me show you this after the contractor here poured a couple of footings. Here is the concrete, you see here, the dowels of the concrete column, these sticks all the way to here only. And then here, you see here the column rebars and the overlap. So you have the 4 rebars inside and then you have some rebars. And you see here, look at the footing. Now you don't see here the hole, right? Everything now is filled with concrete. So at the beginning, we have only dowels. Then after they pour the concrete, they start here to put the long rebars for the column. Now look after they pour the column. Look at the columns here. Here's a concrete footing, a nice column. And then we're gonna have concrete slab above all of that. So we have some like dowels, we have some hooks with some good length here to provide this good connection between the concrete slab and between the column. That was another project. And look what happened here. We have formwork for the wall footing. And we have just done it from inside. How about from outside? Look, there's a soil. And you have all of the 3 bars that sticks out because you're gonna have concrete slab on grade on the top. So you'd like connect them to each other. And this actually is gonna be a trench. So that was a trench. And this is actually like a car wash facility. And you're gonna see here lots of pipelines that sticks above. And this trench is gonna be all covered with steel plates, and this is to drain the water inside the car wash. So you're gonna see here that we have here more formwork, you know. This is another project. I don't know if you guys are aware of landfills and what happened there. You need to have a flare to burn the methane gas. And this is here one big giant footing. And you see here that we have formwork for the entire footing. Right? So they provide here formwork for the entire footing. Different construction, different type of project. And it was only one footing, but the footing was really big. I mean, look at the size of it. Here's the flare, and here's the concrete footing after they poured it. Just, you know, the height of this flare is about 60 feet, and the weight is about 50,000 pounds. It's all supported in this one single footing, and this footing size is about 20 feet by 20 feet. So it's really a big mass here that we are using. It's empty from inside, and you're gonna have here lots of pipeline coming, and this pipeline, the size of it is about 4 feet. So it's really a big structure. It's not really a simple structure, but it is, when it comes to details, it is much simpler than a regular building. So this building here, I would say that this is gonna be more complex when it comes to details. This one here, it's just giant, but it has lots of things, as you see it here. Now let's see how do we size the footing. So to size the footing, to come up with this size, it means that you're going to be doing here soil design. You are not really doing here concrete design at the first step. So when we come to foundation design, I'm going to have here 2 sections for it. The first section is going to be soil design. Come up with the footing size, length by width. The second section of it is going to be concrete member design. So in our course here, I'm going to be covering both sides so that you understand where is this pressure coming from. When you do the soil design, you do ASD design. Do you guys remember the term ASD, allowable stress design or strength? Anyone remember this term?
Yes.
Okay. Anyone doesn't remember the term ASD, allowable stress design? Okay. When you do allowable stress design, it means that your load has no factors. Most likely, you don't add any factors. You do it at the service level. So what is the service? It means when you have dead load and live load, you just add them to each other. If you remember, when it comes to concrete design, we're doing the 1.2 and 1.6, right? 1.2 dead load and 1.6 live load. When you do the soil design here, you don't do that. You just do the service level. What's the service level? It means that you add the dead load to the live load, and this can be it. This should be sufficient. So as it says here, the area required is going to be equal to the P service demand divided by BC. What's BC? Is going to be allowable bearing capacity or allowable bearing pressure of the soil, Q allowable. This equation means that this pressure is going to be equal to the P load divided by the area. But here I'm trying to find out the area needed or required for the footing. So I'm going to be taking the service demand as is divided by the allowable soil pressure that I'm going to be taking it from the geotechnical report or soils report. And with that, I'm going to have the minimum area that I need to use. Of course, the final area, my choice, is going to be a little bit larger because I want to be sure that the actual stress, which is Q, which is P over A. Now, this A in this case is going to be the final A that I provide for the footing, is going to produce stress, which is going to be lower than Q allowable. I have one example. They give you here column dead load 850, live load 560, and say that we're going to have a square footing. The soil bearing capacity or allowable soil pressure is going to be the same term, is 7,000 psi, pound per square foot. And I say what's the most economical size of the proposed footing. Okay, it says square footing. So is this a trick? I'm going to say kind of, yeah, which means this cannot be the answer, right? Because it says here square footing. And this one also doesn't apply. So I'm going to have either 15 by 15 or 18 by 18. Let me see what I can do about this problem. First, I need to find out the service demand. I have dead load and live load. Here's a dead load 850, live load 560. Add them to each other. I'm going to have here 1,410 kips. This is going to be what? The service demand. The required area is going to be equal to this number divided by 7 KSF. What is the 7 KSF? Let me confirm this. It says here 7,000 PSF, which means 7 kip per square foot. Since my load here is getting kips, it is easier to put this in KSF. So I took this 1410 divided by 7. I need at least a contact area between the footing, which means in plan is going to be length by width, it's going to be 210 and fraction square feet. Find out, because it says here square footing, the square root of that number, right? It says here 14.2 feet. I cannot use here 14.2. I mean, construction-wise, besides how certain you are when it comes to the actual load that you're using with, you're working with here. What happens if the live load is slightly higher? So I'd like to go slightly higher when it comes to the footing size. So I'm going to be going here with 15 by 15 feet. Contact area, 225. More than this number, right? So I'm good. I provided more contact area than needed. So I'm not going to be talking about this size of the footing because it's not square, right? So I'm going to be going here with 15 by 15. Now, someone's going to ask and say, how about the actual soil pressure? You can say actual soil pressure, I need your help with. You can say Q equals P. How much is the actual load? Can someone help me here? How much is the actual contact area?
1410.
2 to 5?
Sorry.
2 to 5?
Yeah, 2 to 5.
Okay. How much is this pressure now?
6.26.
KSF, K per square foot, right? Is this lower than 7 KSF, which is allowable? You're gonna say yes, I have good room. Good, my design is good. Are we good? Questions? All right. Now I have some footings. They support vertical load and moment. You can say like which footings? I'm gonna take you back here to our pictures to tell you which footings would be supporting vertical load, just vertical load, and which footings gave you supporting vertical load and some moment. This footing here is designed for only vertical load. No moment on it. Why? Because this is a gravity column, does not support any moment. But look at this footing here. We're gonna say yes, total load is gonna be coming downwards like this, right? But this structure here, if you have an earthquake, the earthquake is gonna be generating horizontal load, like here, for example, it's gonna be some load like this. Or it could be also in this direction. I don't know, because it depends on the earthquake direction, right? And if I'm gonna say the earthquake load is gonna be coming this way, it means if you take this horizontal load applied by this height, the moment R is gonna be generating some moment on this footing along with this applied vertical load. So in this case, this footing here is designed for vertical load and moment. So the moment is going to be causing some stresses on the soil, and also the vertical load is going to be causing some stresses. And I need to find out the combined effect of this vertical load and moment on the footing size and on the stress on the soil.
How do you know one column is going to be supporting, it's going to be only a gravity, and then the other one's going to be also earthquake?
Okay. If I have a moment frame, like seismic resistant moment frame, this seismic resistant moment frames, they are designed for moment and axial load. But if I have only gravity column, which means supports only dead load and life load, do not support any earthquake forces, they're going to be designed only for gravity, vertical, axial load, no moment. How do I know it? Because I did the design of this building. So I know exactly which columns I use to be gravity and which columns I use them for moment frames. Now, why would you have some moment frames at some places, right? Why wouldn't you have this to be a moment frame? It's going to be based on the layout and the complete design of the entire building. So it's going to be a kind of design issue. Like if you like to do something like this, you need to know where the moment frame is going to be. You need to decide on this, do the seismic analysis, and then decide which column is going to be only supporting gravity loads and which column is going to be supporting gravity loads and earthquake forces, which means more moment.
Thank you.
No problem. So now the load is coming here from two sources, or the stress, the pressure on the soil. It is coming from the axial load and also coming from the moment. This is why I have here two equations. One of them, this is going to be only F sub P, which means the stress is due to the vertical load, due to P load. You're going to call it here F sub P. You're equal to P over A, the contact area. And because I have additional moment, I'm going to say F due to moment is going to be equal to M over S. The moment divided by the section modulus of the contact area with the soil. I'm going to skip this equation for a second and then just jump here to this. By the way, you have here definition of everything. Section modulus BL squared over 6 for the footing itself. So this B and L is given for the footing. Here's definition of B and L. So I have the stresses here coming from F sub P and also F sub M. So from the vertical load, I'm going to have uniform stress or pressure below the footing. From the moment, I'm going to have one side is going to be compression, which is this side. Look, this moment is causing this to go down. So compression is going to be in this side and tension is going to be in that side, right? But did you guys know that soil can take tension? Is this a true statement or a false statement? Can a soil sample or any soil take any tension?
No, only shear.
Wouldn't it
Shear and shear and axial force only, right?
Yeah.
So I mean, a case like this cannot happen. If you have pure moment only, the footing cannot do anything to it because now this foot is going to be lifting up above the soil, and there's not going to be any contact between the soil and the footing. So you need some axial load here to balance the footing. You cannot just have moment and a footing. Only moment, no footing is going to be able to help you out, right? Because guess what's going to happen? The foot is going to be lifting, and the contact area between the footing and the soil is going to be only this. And if you take this and start to do another analysis for it, it's going to be much smaller. And you'll find out that no footing is able to support only moment. You need to have an axial component. So I'm going to be saying here, but in reality, I'm going to have moment and axial load. And the stress at this side, I'm going to call this side to be 0.1, right? And this side, I'm going to be calling it here 0.2. The final stress at this side here, at 0.1, is going to be equal to Fp subtracting Fm, because this side, the stress here is going to be the same as here. And the stress at 2 is going to be equals to Fp plus Fm. Both of these two sides are going to be compression. So what you need to do is take 0.1, right? Which is the same as this point, right? It's the same point. And here's going to be 0.2, which is the same as this point. So if you want to find out the final stress due to axial load and due to moment, you need to add the stress from this component, from the P force, plus the component from the moment, right at this point, at the 0.1. And for the stress at 0.2, you add the Fp, and then you add it to this Fm. So one side is going to be additive, which means the compression side, and this side is going to be subtractive. This is the reason that I'm going to be talking here about this equation, the last equation. It says here in the last equation, the stress is going to be equal to Fp, which means P over A, plus or minus Fm. Why plus or minus? Because at one time it's going to be additive, the compression, and the other side is going to be subtractive. So let's move here to this picture. Now, which side is going to be additive? Side 2 or side 1? Side 2, absolutely, this is correct. Thank you, Eddie. So side 2 is going to be additive because here you have compression. And in this side, because of the moment, you're going to have some compression here and tension here. So the question is, finally, at the end of the day, if Fp in value, just in value, is more than Fm, this can be good because Fp plus Fm is going to be new higher force, and Fp, the compression, is going to be more than the tension. It means the footing is not lifting up at all. So now this force P is able to balance the footing. And you're going to have a situation like this. Now the stress here is going to be compression, compression, and the stress on this side is going to be mainly compression coming from the P force and some tension from the M force, this bending moment, right? So in this side, it's going to be higher than this side when it comes to the amount of stress. I said, okay, great. So what I'd like to see is something like this case A, when Fp is more than or equal to Fm, just in value, only in value. All right. Now the big issue or the problem is going to happen when this axial load is not big enough. So the beam is going to, or the footing is going to start to lift up from this side. When Fp is smaller than Fm, what's going to happen? You're going to be looking at this case. When Fp is smaller than Fm, the footing here is going to start to lift from this side. And this is going to be the location. This location is not necessarily right below this area here, but I'm going to say, let's say about here, right? Like in this picture. Look at this picture here. It means this section of the footing is already lifting up. There is no contact here between the footing and the soil. This is why you see no stresses. And the stress is going to be only in this side. It's going to be all pressure, like compression. So, okay. How do you do here the eccentricity? If you like to do eccentricity analysis, you say M over P is going to give you this E, which means this system here, M and P is going to be equivalent to that system here, structure analysis. This E, again, is going to be equal to this moment divided by P. So, okay. Now, figure out the distance from the end of the footing to this concentrated load, call it X. You understand that the stress below the footing is going to be this triangular distribution. And the pressure coming from the bottom is going to be right here. It needs to be aligned with this force, right? It has to be aligned with it. Otherwise, this foot is going to be rotating. You cannot have this footing here to rotate. It means it's going to be unstable. So if the distance here is going to be x, and this here, this triangular distribution of stresses, this force here, it has to be at the CG of this triangle. So this is going to be x. How much is this? It's going to be 2x's, total of 3x's. All right. And in this case, here's an equation to find out x. It's going to be 1/2 of L subtracting E. It's going to be 1/2 of L subtracting this E. And the stress, which is the height of stress in this side here, can be given by this equation. If you just take this force P and put it here on this side, on the soil, you're going to say this force P is going to be equal to 3x times F1 times the width of the footing perpendicular to this slide. I can call this B if you like. It's called here B. So the stress is going to be equal to 2/3. You should be able to find out this equation or to drive it yourself if you're going to be doing one of this soil mechanics classes or foundation design classes. Now the stress here can be given by this equation, and you don't really need to do m/s and p/a. So if p/a and m/s, the standard equation is not going to give you this case 2a. In this case, you're going to be at case 2b, and this gives you the stress equation. This gives you both of these two equations, 5 and 6. Want to find out the eccentricity? You have an equation here for it, m/p, right? This gives you the two cases. If the stress value due to axial load is going to be more than Fm, you end up with this case 2a. If F sub p, which means that you don't have enough axial load to balance this footing, in this case, you're going to have something like this, and the foot is going to be lifting up. No contact between the footing and the soil in this case, in this side, and the pressure, maximum pressure F1 is going to be given by this equation. Any questions? All right. We have this example on finding out the stress below the footing. I would prefer to stop here at this point and talk with you about your homework. You guys see the homework?
Yeah, I did.
Yeah, just right before class.
All right. Let me go to it. Here's a bridge design. And I'm going to be asking you to do this. I mean, the deadline I extended. I don't want to do it like this weekend. I extended it to right after your break. But of course, if you can finish it now and submit it, by all means, go for it. This is here a reinforced concrete section of a bridge. You have bottom rebars, and then you have also top rebars, right? Concrete strength, it says 4,000. ASTM is grade 75, which means F sub y is how much?
75 PSI.
Good. And beta 1? 0.8, just in case, if you forget. I have here two problems. The first one for the positive moment. What does it mean by positive moment? Tension at bottom, correct? What does it mean by negative moment? Let's say tension at top. For each one of these cases, if the tension is going to be at the bottom, it means it's going to be AS, and this can be like AS prime. But look at this. You have here 12, and here you have 20 of the same rebar. You say, how about this hollow area? I'm going to say, don't worry about it. you can just add this 4-inch and this additional 4-inch and this additional 4-inch to be like this, as if what you're looking here at is exactly like this. Someone's gonna say, I have never seen anything like this before, right? And just continue this way.
Make it like into a T-beam.
Yeah, exactly. It is a TB. Very good. Right. It's like this. If here's some bottom reinforcing, it doesn't matter if it's gonna be distributed or just concentrated here. Just a TB. And now, after you're done with this, because you're doing here the positive moment, you can do it exactly the same way. And you say, this now again is gonna be my TB. It's gonna be something like this. Right? It's gonna be here the width of the flange. This when it comes to which moment? Negative moment. When the tension is given in the top, compression is gonna be here. Now, for each one of these cases, it says determine the effective depth of the beam. I'm gonna say effective depth. Now, this is gonna be right in the middle. You see this 6 inches, 3 inches above, 3 inches below. This is gonna be right in the middle. This one here is not in the middle of the slab. Should I write a note here to you guys? I say here, this distance from here to there is gonna be 3 inches. But this distance is given at 2 1/4, so it is not really in the middle of the slab. You need to figure out the depth of the compression block. Now, when you do the positive moment, you need to find out A. And in this case, this is going to be AS times Fy, the 75 KSI. And then look here for the compression block depth, A. If A is going to be here, this is great because it becomes a rectangular section. And this is going to be the compression zone, this area here, based on this 6 feet. So the good thing about this, that this 6 feet is going to be using as your B, the width that's used in your analysis is going to be 72 inches. If you end up with something like this, you're done. The rest is going to be so easy. Now, when you do here the positive moment, which means tension at the bottom, do you really need to consider this to be compression? Let me see here. It says consider the effect of the compression reinforcement. So you're going to have here AS prime. So you need to be careful on the way that you design this. When it comes to the negative moment, you're going to be repeating the whole thing. Now, this is going to be your AS, and this is going to be your AS prime. And the width in this case, when you do the negative moment, this is going to be your B. So I'm going to say in this case, B, let me put it down here. B for the width, right, is going to be equal to 72 inches. And in this case, B is going to be equal to 48 inches. The rest of it, you guys, you have done this before, and you know how to deal with compression, you know how to deal with tension. And I want you to know that the importance of this problem here, when you see a shape like this, I want you to be trained for it. So when you see it later on, sometime, during an exam, during another thing, you're not surprised. You have seen something like this, and you know how to deal with it. So when it comes to your homework grade, there's going to be only 10 points. But when it comes to your understanding to how to deal with similar sections and similar beams, it's going to be really critical for you. Does it make sense?
Yes.
Yes? Okay, very good. Now, second homework. Which is something that you guys can do it very fast, I hope. Also, I want you to be exposed to this type of problems, that you have seen it, so you know exactly how your exam is going to look like. You have this interaction diagram given to you, right? It's going to be doing the same time, but if you want to finish it earlier and submit, it's going to be up to you. You can finish this tonight and just get over it. It tells you here that here's the interaction diagram, right? So we did it for you. And you have 7 stories on the roof, and they give you tributary area of the column, 600 square feet. This is not just feet, this give you square feet. You have the roof dead load, right? And then you have the roof life load. Then you have the floor dead load and the floor life load. And they tell you this is just the total dead load. Don't add anything else. Just give you the values here. So here's a test for you. Can you find out the axial load demand at the bottom of the column after you consider here 7 stories on the roof? Meaning you can create a quick, if you like, equation or a small schedule here. Let's say here's the tributary area, dead load, life load, times 7, because you have 7 typical levels, and 1 roof, and figure out total dead load and total life load at the bottom of the column. After this, you see here it says determine the service, design service load, which means P dead load and P life load, and you do the ultimate load. How do you do here the ultimate load? This is going to be the 1.2 dead plus 1.6 life versus 1.4 dead, right? And it says here show analysis. Show analysis, you cannot just write here the 2 final values without showing me some analysis, right? So I want you to be trained for this language here. In the second problem here, it says advice of the column can support the ultimate load demand above. You see here any moment, there is no moment, which means it's going to be only axial load. And then it says here, no analysis is needed. You're not going to be running the code equation for the axial load. You don't do AG and AS and FY, and I don't want you to do any of that. I'm just telling you here, we have done this for you already. So what you need to do is to indicate if this column is okay or not good, and mark this on the chart, which means that you're going to come here. Let's say your axial load was right there. So you're going to say, here's my axial load. This column is okay. Or you come and then you say, my axial load is going to be here. Axial load demand is here, which is going to be higher than this chart, and therefore it is not good. So I want you to mark it on the chart exactly the way it says, right? It says no analysis needed. You need to indicate what? If this column is good or not good to support this load. And number 2, all right. I see here that some people start to work early. Very good, Eddie. All right. Maybe you can finish it by the time I'm going to finish. And then you need to mark it on the chart. There's 2 things. You cannot just mark it on the chart and say, oh, I marked on the chart and you know it's going to be above, it's not good. No, you cannot do it this way. You need to indicate and mark on the chart. There is a point for indicating this, and there's another point for marking the chart. If you say it's not going to work, and then you put the value, but you did not mark on the chart, you're going to be losing some points. So be careful in exactly what you're reading and what you're going to be providing as an answer to this problem. Advice of the column can support combination of 600 kfoot and 600 kips compression. No analysis needed. Indicate a mark on the chart. Okay. 600 kips. Where's the 600 kips? Someone help? 600 kips here. 600 kip foot. Is the column okay in this case? Yes or no?
Yes.
Good. All right. And do I need to mark it on the chart? Yes, I need to put here a small circle or something. Let's give you right here, right?
Is it okay if we do like the lines like that?
Yeah, do it and then put a circle. And then you need to do something if you like to do. Are you planning to use Adobe or your tablet or what?
My tablet.
iPad? Okay. So in this case, you need to say this is going to be 600 kips, right? And what's the other value? Actually, it should be like the X first and then the Y. You can say 600 kip foot and 600 kip. And which problem is this? I'm going to say this is going to be for problem number 3. I'm going to say, okay, this is going to be for problem number 3. I need to do it this way, right? Is it 900 kips or 600 kips? 900 kips. Thank you. I don't want to show it for 900 kips. I just want to show it for, but if you like. Yeah, it's going to be here, which means it's not going to be good. Now I solved you a few of them. All right. So it's going to be 900 kips, which means it's not going to be good, right? So what I'm trying to say here, you need to show enough information in your answer, in your response. Don't just say this point here is going to be 600, 900, and then you come at the bottom and then you never say anything whether this column is good or not good. And then you say, I answered it for you. I put it outside of this envelope, therefore it's not good. I'm going to say this is insufficient. This is not good enough. What you need to do is to mark it on the chart and come here in the problem itself and then say not good. Or if you like, you can do the whole thing on the chart. You can say in item 3, I can say it like this, not good. This column is not good. And here's the force value, and this gives you the point. I'd say, yes, you provide the information. You say it's not good, and it's going to be for problem number 3, and then you show me the 2 coordinates, the moment and the axial load. Are we good? I want you to know that this is going to be something very similar to it. It's going to be in your second midterm and in your final. And if you are not answering this in details and sufficiently, you may lose points. And in many cases, I mean, I've seen people who knows exactly what they're doing, but they don't provide enough information because they don't read well. And they don't, because someone can just put it here for me, but he doesn't know if this is good or not. Or someone can say it is not good and say for 600 and then just put it in the manuscript in the text. He's going to be saying 600 and 900 kips. It's not going to be good, but he may be just taken from any other source. Or he's just shooting in the air, shooting in the dark, as they say. He doesn't know. He was not sure if this is going to be good or not, but he decided that this is not good. How do you decide it's not good? When you show it on the chart. And then you write down, or you write here that this is not good. The rest of the problem is going to be so simple because I have, look at this, maximum tensile strength of the column with no moment from the interactional diagram above, no analysis needed. Which point am I talking about here? Can someone tell me where should I go? Is it this point? Yes? No? This point? Here? Is this a point with no moment?
No.
This point here is maximum moment, right? This can be like when you have no axial load. This can be the point. So what you need to do, you need to find out this value roughly, and you need to mark it here on the chart. Some people can just get the value and you don't mark it on the chart. So I'm gonna say you don't know exactly which point. You're just lucky that you went very close to it. So you need to come here and say, okay, which problem is this now? Let's give you problem number, maximum tensile, let's give you number 4. I say, okay, this give you problem number 4. And the value is equal to, let's say, 310 or 3 whatever, 320 kips or so. You need to figure this out yourself. And then you mark it right here. Now I understand. You know exactly which point. For number 4, you mark it here, this can be for number 4. And then you put a small circle around this. And then you put this arrow, and then you put the value. You understand what you're doing. Versus another person who just write the value at the bottom. It's going to say 320 kips without marking the chart. So please be careful about everything that's written here because for each one of them, you're going to have a point. All right, I'll let you go. Enjoy your spring break. And stay safe.
Thank you.
Hey,
All right.
thank you.
Thank you. Yeah, I will try to answer emails, but you'd excuse me if it comes a little bit late. This is why, please, if you have any questions, try to have it right away.
Hello, Professor.
Yeah, I'm here.
Oh yeah, I made it after you took roll for this class.
Oh, do you have questions or so?
Oh no, I thought that you like reflect on the instead of it being like, oh, absent, you put like tardy
Okay,
Yeah.
all right, hold on.
for the grade.
Okay, let me see the absent people here according to this. Omar and Angel,
Yes, Angel.
all right, I put you here, Angel. Blake and Jasmine. Jasmine is here, I've seen her. Jasmine. Okay, all right.
All right. Thank you. I appreciate it.
Thank you.
Have a nice
No
week.
problem.